Okay, so last time we sort of introduced radiation and talked about black bodies. We talked about specifically how in this class radiation is going to be studied only from the standpoint of we'd really like to be able to do radiation heat transfer problems, which means I'd really like to be able to look at a set of surfaces at different temperatures and understand how they're transferring energy between themselves by radiation because it's a heat transfer class. So in the end, in order to do that, we're always going to be looking at a surface and thinking about the difference between how much energy is leaving that surface and how much is coming in, because that's going to be the net heat transfer to that surface. So that's the difference between emitted radiation and absorbed radiation. Last time we talked about emitted radiation and said that there's this hard and fast upper limit that's called a black body. And we said that this is actually probably the easier part of the problem to think about because it really just depends on what the surface itself is doing. Today we're going to start thinking about the absorbed part of the problem. The absorbed part of the problem is complicated because it depends on what are all of the other surfaces that are around this surface, what direction are they pointed in, what do they look like, what is their temperature, what are their properties, all that kind of stuff, because that then tells me how much radiation is going to be incident on this surface, and then the surface itself can absorb some of that radiation and reflect some and maybe even transmit some. So black bodies are particularly useful as a place to start for this conversation because not only do we know exactly how much do they emit, right? They emit according to Planck's law, sigma t to the fourth. We also know that if I want to know how much they absorb, all I have to do is figure out how much radiation is incident on the surface because they're going to absorb all of it, right? That's what makes them look black, is nothing gets reflected, so everything gets absorbed. So we still do have to figure out, though, how much radiation is incident on this surface, and that calculation is made easier or facilitated by this thing called a view factor. So the view factor, Fij, is this geometric quantity, at least for diffuse emitters, that is the ratio of how much radiation leaves surface I and goes to surface J divided by the total amount of radiation leaving surface I. So if you look at this picture here, it's the ratio of how much of this total energy actually goes off and hits surface J versus the total amount of energy, right? So it's going to be a number that's between 0 and 1. 1 being the situation where all of the energy emitted by I hits J. In other words, the surface I sees nothing but the surface J. 0 being none of the energy emitted by I hits J. So that would be the limit where surface I can't see surface J at all, right? So when we're doing these problems, a big part of the radiation problem is going to be trying to figure out these different view factors, right? And there's going to be a whole set of them, for every surface. Between every surface and every other surface. We have a few tools that we can use. One is inspection, which is basically just saying it should be obvious in some situations what the view factor is just by thinking about it. There are libraries and libraries of these view factors that people have already tabulated for you, and those are super useful. I'll show you a couple places to find some of those. There is this view factor integral that you can just do in general for any two surfaces. It's a double integral. We're not going to do it in this class, but I'll show you what it looks like. There are these useful view factor rules, in particular the enclosure rule and the rule called reciprocity. And those rules are helpful in that they let you turn maybe just one or two view factors into additional view factors. So they're relationships between view factors. We won't talk about this today, but we'll come back and talk about the crossed and uncrossed strings method, which is a super useful way to get view factors for situations that are two-dimensional, or at least can be approximated as being almost two-dimensional. And then finally, this last one is a really powerful technique called the Monte Carlo technique, and we'll talk about that as well. So let's start with inspection. So inspection is basically just looking at the situation and seeing what view factors are kind of obvious. So for example, in this particular situation, the view factor between 1 and 2, so F1 to 2, should be pretty obvious. It should be obvious that all the radiation that leaves surface 1 here has to end up hitting surface 2, right? There's nothing else. There's no other surface that surface 1 sees. So F1 to 2 equals 1. 100% of the radiation leaving 1 hits 2. F1 to 1 is 0 for this case, right? There is no part of surface 1 that can see itself. It's completely, convex, I guess, right? It can't see itself, so F1 to 1 is equal to 0. F2 to 2 is not equal to 0. So if I come out here on this surface, which is the inner surface of the cylinder, surface 2 can see itself, right? If I'm standing here at this point, I can certainly see other parts of surface 2. So F2 to 2 is not 0. And F2 to 1 is not 1, right? It's not true that 100% of the radiation emitted by surface 2 will hit surface 1. Some of the radiation emitted by 2 will hit itself, right? So there are things that are obvious you can do by inspection and things that you just can't. We said that there are these view factor libraries, and they're pretty useful to know about. So a couple places you can find these. One of the more, let's see if I can bring up my web browser. So one of the more comprehensive view factor libraries is this website put together by John Howell, who's a professor at the University of Texas at Austin. And if you click table of contents, you'll see he's divided his view factors up into differential to differential. So these are really handy if you want to do integration to try to get view factors, or if you want to split your surface up because it's maybe not isothermal. This is differential to finite area, and this last one is finite area to finite area. And then he's tried to divide them up into what kind of areas are we talking about, planes and rectangles or discs or cylinders or so forth. So if I click on, let's click on discs. Then I get this whole list of different situations. So here's a circular disc to a parallel right triangle, right? Here's a disc to a coaxial annular ring. So if I click on this, I get a picture that shows me what's going on. And in some cases I get a formula, and in some cases I get actually a chart or a table of data. But some way somebody has looked at this problem for you and given you the solution, right? So that's a pretty nice place to find view factors. If somebody's already looked at your situation, there's no reason for you not to use that solution. Most of these are programmed in ease. So if you go to options, function information, you go down here to heat transfer and fluid flow, there's an entire library called radiation view factors. If you look at this library, it's organized kind of the same way. I have two-dimensional view factors. There's not very many of them programmed because they're so easy to get using the crossed and uncrossed strings method that there's no real reason to build some big library of these. There's differential view factors that are more useful, but there's a whole bunch of three-dimensional view factors. So if I click on three-dimensional and just start scrolling through here, you'll see there's just a whole bunch of different situations. And if you want to look at them all at once, I think it would be index here, and you can bring this over here, and they're divided up kind of the same way. So we have rectangles, cylinders, discs, spheres. If you look at discs, you can see all the different situations that have been programmed. Here's the one we were just looking at in Siegel and Howell. So if you click on this, you get information about where it came from. And I guess I would say the only trick to using these is you do have to make sure you understand which surface is the from surface and which surface is the to surface. So in these, the surface labeled 1 is the surface the radiation is coming from, and the surface labeled 2 is the is the surface the radiation is going to be incident on. So F1 to 2 is what fraction of the radiation emitted by this disk hits this concentric parallel ring, right? It's easy to mix those up, but you'll get the wrong answer if you do that. Okay, so let's go back to here. So that's another way of getting view factors. I said there is this view factor integral, which lets me get view factors between any two surfaces. So if I have a surface I and a surface J, I can do this sort of big, ugly, complicated double integral over here, where I, divide surface I up into a bunch of differential areas, and for each differential area, I'm going to integrate to a differential area on surface J, and then it's related to what's the distance between those differential areas and what's the angle between the normal to the surface and the vector that joins those two differential areas. So that's possible to do. It's complicated. I wouldn't expect you to do that in this class. We used to have a 700 radiation class, a 700 level radiation class. I think it was 766. That would be sort of the place you might do something like this. All right, so those are at least 3 different ways to get view factors, and we'll talk about a couple more, not today, but later. But the other way to get view factors, basically from view factors, is these different view factor rules, right? So this is a way to take some set of view factors and use them to calculate other view factors in your problem. So one that's pretty easy to understand, I think, is this thing called the enclosure rule. So an enclosure is a set of surfaces that completely enclose the radiation, right? There's no way radiation that's emitted by any of these surfaces can go anywhere but to any other of these surfaces, right? That's an enclosure. So if I have an enclosure, then basically I can write that all the radiation emitted by a surface has to go somewhere, right? And in view factor terms, what that's saying, for example, for surface 1 is that the fraction of the radiation emitted by surface 1 that goes to surface 1, so F11, plus the fraction that goes to 2, so F12, plus the fraction that goes to 3, F13, has to be 100%. It has to be 1, right? So F11 plus F12 plus F13 has to be 1. And I can write this for any surface. I can do the same thing for surface 2. So F21 plus F22 plus F23 has to be 1. And in general, I can write this equation for every one of my surfaces, right? And what that lets you do is, if I'm working on a problem and it has, let's say, 4 surfaces, if I get 3 of the view factors for one of the surfaces, then the 4th one I can get from the enclosure rule. So I think that's pretty intuitive and obvious where that comes from. The other one that is really handy is called reciprocity. Reciprocity, I think, is less intuitive where it comes from, and the derivation of reciprocity also leads into nicely our fundamental formula for how black bodies exchange radiation. So let's go through that derivation kind of carefully. So reciprocity you get by thinking about two surfaces. We'll call these I and J. Okay, so surface I is a black surface. It has some area and it's at some temperature Ti. Surface J is also a black surface. It has some area and it's at some other temperature T sub J, right? And I want to think about what is the radiation heat transfer, the net radiation heat transfer between I and J. And that's going to entail 2 different components, right? There's going to be some radiation emitted by I that ends up at J and is absorbed. So that's the stuff going from I to J. But then coming back, there's going to be radiation emitted by J that ends up at I and is absorbed. So that's stuff going from J to I. So if I want the net radiation heat transfer from I to J, I have to take the first thing and subtract from it the second thing, right? That's going to be net radiation heat transfer from I to J. So let's think about this. If I want to get the first thing I'm going to do is figure out how much radiation is emitted by I. If it's a black surface, then that's just the area times the black body emissive power, sigma Ti to the 4th. So that's emitted diffusely. It's emitted in all directions. And then how much of that actually hits surface J? Well, that's where the view factor comes in, right? The amount of this radiation that hits surface J is equal to that amount of radiation multiplied by Fij. Fij is the fraction of the radiation emitted by I that hits J. So this is Fij times AI times sigma Ti to the fourth, right? How much of this is absorbed by surface J? Well, all of it, if surface J is a black body, because black bodies absorb everything. So the radiation emitted by surface I that hits surface J and is absorbed is this quantity here. If I do the same thing for surface J, I get this equation here, right? Surface J is emitting radiation, Aj times sigma Tj to the fourth. How much of that hits surface I? Well, Fji, and that's all absorbed. So what's the net rate of heat transfer from I to J? It's going to be this stuff here minus this stuff here, right? It's going to be Fij times Ai sigma Ti to the fourth minus Fji times Aj times sigma Tj to the fourth. This first thing is what's going from left to right. The second thing is what's coming back from right to left, right? So this is my equation that tells me what's the net radiation heat transfer between two surfaces I and J.